Hi guys, welcome back to my channel. Today we're going to be looking at action and reaction forces. And this comes from the idea of Newton's third law, which states that every action has an equal and opposite reaction. So this came about because when you are standing on the earth, you are being pushed down upon by gravity. So what then is pushing back up on you? Well, because you are in equilibrium, because you're in a steady state when you are standing on the earth, the force that's pushing up on you is actually called the normal force. So this is the force which has an equal and opposite reaction. So how do we actually find the force of you standing on the earth? So let's say that you are someone who weighs 50 kilograms. Now, your mass is not the same thing as your weight. Your mass is equal to the amount of stuff that makes up you, whereas weight is equal to the force. How do we find this force? Well, from Newton's second law, we know that the force is going to be equal to the mass times acceleration. And in this case, acceleration is due to gravity. So if you wanted to find the force, that's going to be equal to your weight in kilograms times by 9.8 meters per second squared. That's the gravitational force. So this is going to be approximately 500 newtons. Very rough estimate there because that's approximately 10. Since we don't know the mass of this object, I'm going to denote the mass as m, and so therefore this force that's acting downwards is going to be equal to the mass times the gravitational constant. The normal force, since it's equal and acting in the opposite direction, is going to be equal to negative mg. So this is what's happening when we have an object that is on a flat surface. What happens if this object is on a slope? Well, this formula is no longer going to work for us because we've got some other variables to consider here. Now, the normal force is always acting perpendicular to the surface that you're resting on. So in other words, it's acting perpendicular to the slope here. So this is our slope here, and this is our normal force that's acting in a perpendicular direction to that. Our mass is still going to be equivalent to, our weight is going to be equivalent to our mass times the gravitational constant, and this is still going to be acting in a downwards motion because it's still pulling in towards the center of the earth. So how do we then go about calculating the normal force now? Alright, so I've drawn a little diagram here just to show you where some of these values come from. So luckily for us, this triangle is actually a similar triangle to this ramp here. And so these two angles are actually the same. So if I was to resolve this into my two forces, this red line here, this is our force that's pushing down onto the ramp. And so the normal force is going to have the opposite effect to that. So to find this red line here, I just use my cos theta is equal to adjacent over hypotenuse rule. And then once I've found the length of this vector here, I've just flipped it and made it negative to find the equation of the normal force. This force here, this one here in blue, this is parallel to my ramp. And because this is parallel to my ramp, I can calculate the force needed. So if I was, say, for example, dealing with a problem that had friction, friction would be acting in the opposite direction to this force here. So if I wanted to find the frictional force, that's going to be equal to negative mg sine theta. So depending on what we're trying to find, whether that be the frictional force, the normal force, or for trying to find forces that are parallel to our particular object, that will change the way that we use these particular formulas. Let's go ahead and let's do an example. A parcel of mass 5 kg is maintained in an equilibrium. So in other words, it's not moving on a smooth plane inclined at 40 degrees to the horizontal by means of a force acting up and parallel to the plane. Calculate the magnitude of this force and the reaction of the plane. So let's go ahead and draw a diagram to represent our particular scenario here. Alright, I've drawn my diagram here. So just some important information to include. We've got this horizontal force that's acting parallel to the plane. So this is going to be equivalent to our frictional force. So this is what's holding this particular object in place. So in this case, since we're looking for the frictional force, we know that since the frictional force is parallel, it's acting in the opposite direction to this force here. And so it's going to be equal to negative mg sine theta. Similarly, it's also asking us to find the reaction of the plane. So in other words, it's asking us to find the normal force. And we also know that this is going to be acting in equal and opposite directions to this red line here. And so the normal force is going to be equal to negative mg cos theta. So let's substitute in our values and find the frictional force and our normal force. All right, gone ahead and I've calculated our two solutions for these. Now, these have come up as a negative answer. I don't want you to freak out too much when you do get the negatives, because remember, the negative just implies the direction, so it's acting in the opposite direction. So if we were looking for the magnitude of each of these forces, the magnitude of the frictional force is going to be equal to 31.45 newtons, and the magnitude of the normal force is going to be equal to 37.54 newtons. Let's jump into a slightly trickier example now. Okay, so we have the same parcel and it's on a smooth plane inclined at 40 degrees to the horizontal. So same scenario as before. But this time we have a force that's acting at an angle of 20 degrees to the plane. So we need to calculate the magnitude of this force, and we now need to calculate the new normal force or the reaction of the plane on the parcel. So again, I'm just going to draw my diagram and come back. Okay, so I've drawn a diagram which is outlining what's going on in this scenario here. So we have the same forces as what we had before. So we've got our angle of 40 degrees in here and in here, and we have our force that's acting perpendicular to the plane. We have our force that's parallel with the plane. Now, let's say that this is, say, some sort of strap or something that's holding this package up, or this parcel up, at an angle of 20 degrees. So we can actually break this down into its x and y components as well. So again, we have this blue line here, which is parallel to the plane, and we have this red line here, which is acting in a perpendicular manner to the plane. So when we sum up all these forces should sum to 0. So I'm going to go ahead and I'm going to calculate what the value of each of these forces are. Okay, this is starting to look a little crazy. I've zoomed in here. So just to show you what's going on, we've got our angle here. This is our opposite side. So this vector is going to be f sine of 20. This side is adjacent to our angle. So this is going to be cos of 20. This angle here is adjacent to my, I don't want to say vertical, maybe perpendicular force, that's what I should say. So we're going to use cos, and then for our parallel force here, this is going to be opposite, so we'll use sine. So now that we've resolved each of these into their components, when we sum each of these components, they should add to 0. So I've got my components here perpendicular to the plane, so that's including this f sine 20 component, we've got our normal component, and we've got our 5g cos 40 component. Similarly, with our parallel components, we've got this f cos 20 component and 5g sine 40 component. And so when we sum each of these, they should sum to 0. Right, these forces are these forces are acting in opposite directions, so they are going to be subtracted from one another. These ones are acting in tandem, so we'll add those, and then this is being subtracted because again it's acting in the opposite direction. So now that we have that information, we can go ahead and we can solve for f. Once we solve for f, we can substitute that into our next equation and use that information to solve for n. Okay, so our value for f ended up being about 33.5 newtons, and our value for our normal force ended up being about 26.07 newtons. This seems pretty reasonable to me, because if we think about it, this force that's acting here is going to weaken my normal force. It's taking on some of the load of my normal force. So if we scroll back up and compare that to the last question, the value of that normal force was about 37.54. So that seems pretty reasonable to me. Alright, so that is how we use vectors and vector resolutions in order to solve these sorts of problems where we have forces that are acting in tandem with one another. So my biggest tip for this one, I think, is number one, draw a diagram, and I think draw it a lot bigger than what I've drawn it so that you can actually see what's going on. And number two, I think using colors, I know particularly helps me to identify which forces are acting in tandem with each other and which forces are acting perpendicular to one another. All right, guys, that's my video on action and reaction forces. I'll see you in the next one.